A matrix can look like a mystery box. You feed in a grid, and out comes a stretched, tilted shape. So the question is, what is the matrix really doing? QR decomposition gives a very clean answer. It says every well-behaved matrix can be written as A equals Q times R. Here, Q is orthogonal. That means Q preserves lengths and angles, it is the pure rotation or reflection part. R is upper triangular, so all the action is above the diagonal, like a staircase of coefficients. A great way to picture this is with the columns of a Gram-Schmidt takes those columns one by one and makes them orthogonal. First we keep the direction of the first column. Then for the next column, we subtract the part that points along the first one. For the next, we subtract the parts along the first two. The orthogonal directions become the columns of Q, and the projection numbers get collected into R. Why is that useful? Because solving AX equals B becomes much easier. If A is QR, then AX equals B becomes Q or X equals B, multiply both sides by Q transpose, and you get R X equals Q transpose B. And because R is triangular, you can solve it by back substitution from the bottom row upward. So QR decomposition is really a split between geometry and bookkeeping. Q handles the twist. R handles the steps. Together, they turn a messy matrix into something you can actually work with.